Hi, it's Terry Dennery of the MathWorks. So we're starting off exactly where we left off in the previous video, which is that our feed-forward strategy for calculating the torques required to get the movement we want from our prescribed motion robot does not work. Okay, it does not work because essentially we have three, well, if you look at the robot, perhaps you can see it, one, two, and really three inverted pendulums all stacked up on top of each other. It's a substantially, I'd say, unstable mechanical system. All right, and that even the smallest of errors, that what we're really doing is identical mechanical model being used in our controller, meaning all the masses, geometry, inertia, all that kind of stuff is exactly the same as what we're representing the real robot with our plant model. It's all the same, and it means that on this computer that the error of calculation, which is numerical error, probably on the order of 10 to the minus 16th, is enough to trigger it into an instability. All right, and so in other words, 1 e to the minus 16th becomes very big very rapidly. And so as soon as what we think is happening in our controller departs, and it's basically is what we think as set up in our command signal here. What we think is happening, as soon as it departs from what's really happening here, all the calculations of ideal torques will be gone. It's not a good calculation at all. And that's the point of feedback, is that let's make sure that what's really going on in this robot continually is being informed into what the controller is doing. And that's the nature of feedback, and it's why it works so well. So what we have right now is we do at the upper level have a feedback loop, but that's just feeding the port here, which you'll see is not being used in the calculation at all. All right. Now it is a feedback of a bus, and as a shortcut, I'm going to just copy this bus selector in. All right. I'm going to double click on it. You'll see that what's being reported in our feedback has different names than what was reported in our command. So we have to kind of clean this up. Oops. All right, so let's delete that. And now it's kind of filled in with the important feedback information. And what we're going to do here is going to be a positional feedback control, and therefore we're going to go into this motion component. All right, and we're going to get it for each of our axes. There we go. Okay, T, T, B, F, A, W, and H. That order, of course, is very important. We keep on making sure we're doing that. All right, and so the idea of the feedback control really is, well, let's look at the difference between the position commanded and what we're getting in our measurement. And so that will be the difference between the two, and we'll use the sum block to do this. Oops. All right, and so having used this block for years, I think that this is the setup I want. And it's going to basically have feedback subtracted off, command being added, and the difference between the two will be the output. Yeah, and that, oops, I got it in the wrong order, because I want a plus at the top and a minus on the left. Okay. Okay. And so that difference between the two, we'll operate on that with the PID controller. There you go. And we'll essentially add it so that the overall control for each of these axes will be the calculation of our mechanical model, what I'm calling the feed-forward control, the inverse mechanics, plus the feedback measurement. All right, and so I'll do a sum block up here too. We'll take that. I recall I kind of fretted a little bit about just calling it control in the previous video, and I wanted to call it torques. But what I realized was, based on the way that that these things get named, whatever. It was kind of a technical issue that prevented that. Well, it turns out we need to open up that bus signal and do something with it anyway. So let's get a bus selector. Double click on this, and we just grab the torque right there. Okay. And this will be the TT, which stands for turntable torque command. All right. And basically we'll do that 5 times, and that'll be essentially the controller. So again, I'm going to kind of go do this, and through some crafty editing, I'll kind of remove all the stuff that's kind of repetitive of what we just did, and we'll be right back in a second with the full controller in place. Oh, I'm going to jump in right now. You'll see I've done 2 of them now. I just recognized an error, right? And this is the whole idea of PVA. Now, PVA, we've talked a little bit about in the previous videos. It's position, velocity, and acceleration. We're doing a position control, and therefore we only need the first component. And so I'm going to use the selector block. Let me type that, SEL. Let's double click, get this up. All right, and so by default, it operates on a 3-component signal, and it takes the first and third. We just want the first one. So let's just put in a 1 there. And the image you'll see will change such that of the 3, we pick the 1. Okay, and because this command is PVA as well, we'll put that in there like that too. And so anyways, I'll be back in a second as I kind of complete this. Okay, so I think I got that. All right, so a little bit of cleanup, a couple of things actually. I think I'll do it here first. All right, default values on the PID controllers we pulled out of Simulink is 1, 1. So KP is 1. The proportional gain, that's what KP is. The integral gain is 1, and the derivative gain is 0. All right. Perhaps I'll do a video where I get a little bit more into kind of where PID comes from. They probably do have a few videos out there on it, and certainly MathWorks does too. But anyways, I won't elaborate on that now. All right. And so I'm going to do something that looks kind of arbitrary. And I'll just say that 10 for proportional gain, proportional gain means that a torque is going to be delivered by this piece that will be proportional to the difference between what we want the angle to be and what it is. All right. And it says that if I had a difference, an error of 1 radian, it would apply 10 Newton meters, which would be quite a bit for my robot. And therefore, 10 is kind of a high value, but certainly I don't expect a error of 10 radians. So anyways, we're going to use that same PID for all 5 axes. All right. And why can we get away with this? Well, I'd say that that's the thing that really a mechanical inversion really is doing for us, right? And one way of saying it is that it's allowing PIDs to do what they were designed to do, which is apply controls to linear systems. That the idea of kind of the inverse mechanics kind of operating on the forward mechanics means that all that nonlinear stuff that really is in existence of the mechanics kind of gets canceled out. That absolutely is a kind of a theoretical idea that I think is very sound and probably very well supported in the literature. All right, so that's the basic idea. I want to say it kind of in the context that PIDs work really well for nonlinear systems anyways, and that's because we got so good at tuning them and even measuring how good we are through things like overshoot and rise time and stuff like that, that we kind of reach a place where we could negotiate and assess that, hey, that's going to be good enough with just the PID. Again, it continues to be a really interesting conversation to have, but my perspective is, well, if it's easy to get that inverse mechanics, let's go ahead and use it. That's what we're doing here. And certainly because of that, we're enabling this idea of, well, it's just going to choose a value of 10, and you'll see that it kind of works, all right? Perhaps we'll have deeper conversations but on this idea of what feedforward is really doing. But I'd say that if my feedforward controller is predicting useful torques, that is only going to be true if the state of this system, meaning the position and velocity of every one of those axes, is going to be identical to the plant. And in a way, that kind of explains, we'll go to the plant, make sure that's true, get that feedback, use that feedback. And with PIDs, basically make sure that the controller and the plant kind of hang together, at least with regard to what their states will be. Okay, so we got 10, 10, 10 on each of those, right? Yeah, this last one, did I get to 10? Yes, we're good there. All right, and now I'm going to just kind of correct these names. So as I produced the same kind of formulation for the additional axes, I reuse that same sum block. And it's through that sum block that the name of the signal is coming from. And so I just need to kind of fix it for the other four. W for wrist. And then finally we'll get to H for hand. All right, so we just reconfigured the bus here. Oops, do not want another port there. All right, and so this signal coming out, now called control torques, but we need to kind of fix that over here. And maybe I'll even kind of change the name here, call it robot torques. And certainly with this redefined bus, this bus selector is going to be very confused. All right, and so we just need to update it. Okay, so these new names, those are coming because it's informed of the signal, and I just click on that and I put them in. And I always want to check TTB, FAW, H. So those look like they're lined up properly. And I think we have it. Let's go ahead and hit run and see how we do. And that looks really good. And that is with gravity on. Right, and just to kind of prove how well it works, this is kind of easy to fix. I'll delete the feedback right there. We'll hit run. And there it's unstable. So feedback's a really good thing. And I'll just hit undo to get it back. All right, so anyways, thank you. We'll kind of continue a little bit more on controls. We'll start talking about kind of discrete, and that's what you're going to have to do when you work with real hardware. And that's kind of why you want to do it with Simulink too. We handle all the, kind of timing of that really well. All right. Anyways, thank you.